This is our PowerPoint on power factor correction, presented by Demantis Burkus, Jack McKenna and Tim Giblin. What is a power factor correction? Power factor correction is a technique used in electrical engineering to improve the power factor by reducing the reactive power present in the circuit. Power factor correction aims to increase the efficiency of a circuit and reduces the current drawn by the load. It reduces the phase shift between the voltage and the current. The most economical value of the power factor is between 0.9 and 1. The task of the project. A car manufacturing facility has installed a new single-phase motor to power an air handling unit supplied by a 50 Hz AC power source. The increase in energy costs is greater than expected based upon their estimation. An explanation and solution must be submitted. The voltage source was 260 volts, overload was 6.16 ohms, inductor load was 18.26 millihenries, cable length was 52.7 meters, and the area was 20 millimeters squared. The calculations that were required. To begin, the impedance of the load of the resistor and inductor must be established. This is found by using the following formula. Z load is equal to R load plus 2 pi times frequency times L, which we got to be 16.6 plus 5.7365 J. Then we had to convert it to polar form, which we ended up getting 8.4174 ohms, angle to 0.7498 radians. After obtaining a value for Z load, the supply load must be verified. To complete this, first find the voltage load using the following formula. I load equals voltage supply over ZT. We found this to be 30.6477 angle minus 7426 in radians. Next we have to move on to the V load equals I load by Z load, which we found to be 257.97 angle 0.0072. This will allow us to find the S load, which we found in polar form to be 7906.187 angle 0.7498, and in Cartesian form 5785 plus J53879. After completing these calculations, the power factor can be established. We use the apparent power, which is 7906.187, and the real power, which is 5785. Power factor can be calculated by dividing the real power and the apparent power, which we found to be 0.73 as our power factor without the capacitor. We can now calculate a capacitor value using the formula LC equals 5387.9 over 260, which we got to be 20.72 amps. We can then calculate XC, which is VC over IC, which is 12.548. The capacitor can then be calculated by using the impedance formula, which we got to be 255.876 microfarads as our capacitor value. We can finally find a power factor with the capacitor included. This can be found by finding the apparent power, which is 13,412.69, and the real power, which is 13,408.90. The power factor is calculated by real power over apparent power, which is 0.99. So wait.
Finally, we found the power loss. We used the following formulas. We got a resistance of 0.1194 ohms for the power loss formula, which was 0.113 watts. And to determine the energy loss, we got 0.041 kilowatts. Given that the energy loss in a week is 0.21 kilowatts per week, and the average price per kilowatt in Ireland is 0.26 cents, our value was €2.84 a year. Here we demonstrated LT splice, and we demonstrated the phase shift between the supply current and the supply voltage, as you can see.